my dear students. Welcome to the classes of advanced econometrics. So, from last couple of weeks, we are discussing about different types of dynamic econometric models and autoregressive model, and how to estimate, or what are the techniques that we can use to estimate a dynamic econometric model, and why we cannot use OLS directly to this kind of dynamic econometric model. And suppose if we use an OLS or ordinary least square or regression method to estimate this kind of a dynamic equation, what will be the consequences? Okay, so as I told you in the beginning, for estimating a dynamic econometric model, we have a series of different techniques, starting from ad hoc OLS and ending into Almon polynomial distributed lag model. Okay, so a distributed lag model can be estimated using a procedure called ad hoc OLS provided by Alt and Timbergen. Okay, but it has many consequences or many limitation it has. Okay, so that's why Koyak he has converted an infinite lag model into an autoregressive model using certain algebraic technique or mathematical technique. Okay, but this Koyak model has a lots of limitation. The most important limitation was it is purely based on certain mathematical manipulations and it doesn't have any theoretical support. Okay, so adaptive expectation model and partial adjustment model was two theoretical model that is rationalized this Koyak approach. Okay, yes. So after that we discussed suppose if we how we can use Euler's to this uh, distributed lag model or autoregressive models. Okay, so in the equation where the lag dependent variable is there, it is called autoregressive models, and for estimating that type of a models we can use instrumental variable method, or what we popularly known as IV method. Okay, it is nothing but we are substituting or we are replacing the yt minus 1 with xt minus 1, and this as per the instrument variable method, or as per Leviathan technique, this xt minus 1 will be the best proxy for yt minus 1. That is the basic idea behind using the instrumental variable method. Okay, so so we discussed OLS. Then from Euler's we came to Koyak model, and from Koyak we have discussed two different types of models. Okay, then we discussed instrumental variable method. Instrumental variable method is basically a method which is overcome the issue of uh, the what is called the when we use this Euler's method to estimate the dynamic econometric models, certain properties of blue, then not only the estimator will be not only the best, okay, it will be uh, inconsistent. Okay, so in order to overcome this issue we can use the instrumental variable method. Similarly, there we have a Koyak model, and this Koyak model is basically based on certain assumptions. Okay, assumptions like all beta is having the uh, same slope or same symbol or same uh, same, if beta is positive, then all the remaining betas will be positive, and if beta is negative, all remaining beta will be negatives. Okay, so all of these uh, slope coefficient is having the same sign. Okay, similarly they decline geometrically. Okay, so these are all certain assumptions of Koyak model, and if any of these assumptions are violated, then the Koyak model will not work. Okay, so now one more model is left to describe or left to discuss. This is what is called Almon approach to distributed lag model, and this approach is mainly developed as an alternative to this Koyak approach. Okay, Koyak have Koyak method has lots of limitations, and Almond's approach is basically an attempt to overcome the issue in this Koyak model. Okay? Yes. So let us discuss this Almond polynomial approach. So this method was developed by Shirley Almon. Just wait, there's a technical issue. Okay. Yes. Sorry for the delay. So this method was developed by Shirley Almon. He was an American. He's an American econometrician. Okay. So this Almond polynomial model or PTL uh, is just no is a model that is developed to overcome the issues in the Koyak model. Okay. So Almond polynomial model will not cover or will not uh, a solution for all the problems in Koyak model, but the Koyak model is basically depends on only one assumption. The core assumption of the Koyak model is beta coefficients decline geometrically as the lag lengthens. Okay, so this is the core assumptions of the Koyak model. All the betas having the same sign and they decline geometrically. Okay, so but these assumptions may not be valid if you take some real economic data, okay, and if you examine and if you take such as much as lagged values and if you check this result, then you can see that all the betas will not have the same sign and they will not decline geometrically. Okay, some this is the assumptions made by the Koyak. Okay, this is the first one. So this is the first one, second one, third one. They decline in the geometric progressions, but sometime they decline in a reverse U-shaped, okay, or they decline. The beta first the beta value may increase, then it may decrease, okay, or sometimes it may have a cyclical pattern. Okay, so all the betas will not have the same sign and they will not decline geometrically. This was the idea, or this was the idea behind this development of a new model called the polynomial distributed lag models. Okay, so the thing is that Koyak constructed his model based on one assumption: betas decline geometrically. But the Shirley Almon, he arguing that, okay, all the beta coefficient may have some other shapes. They will not decline geometrically. Sometime the beta may increase first, then it may decrease. Okay, or first it may be increase, then decrease, again it may increase. This is what is called a cyclical pattern. Okay, yes. So in such situations, the Koyak model will not work. Okay, so if this lagged coefficients is behaving like this, okay, U-shaped or reverse U-shaped or cyclical pattern, in such situation the Koyak model will not work. So what to do? Okay, so in such situation, surely Almon suggested we can express beta as a function of the lag length. Okay, always the coefficient of beta is a function of the lag length, and if we fit suitable curves to reflect the function relationships, okay, then if we know if we can express the beta as a function of lag length, and we can fit suitable curve to reflect these functional relationships. So first what we have to do is we have to understand the relationship between the betas and the lag length. This can be understood by fitting certain suitable curves. Okay, yes. So Almond models it allows for any lag structure. The lag may be uh, if the lag may be U-shaped or inverted U-shaped or cyclical pattern, whatever may be the lag structure, Almond's model allow us to build a model. Okay, so the basic idea behind this Almond's model is any lag structure can be approximated to a polynomial of degree at least one more than the number of turning point in the function. So what we have to do? First, we have to fit a suitable function uh, to uh, to get the relation between beta and the lag length. Okay, and after that, this relation can be approximated by a polynomial of degree at least one more than the number of turning points. What is this turning points? For example, suppose if we understand that the lag structure, the beta and the lag length, they are having a U-shape or inverted U-shaped relationship. Okay, so in an inverted U-shaped relationship, how many turning points are there? There will be only one turning point is there. Okay, so for an inverted U shape, it is having one turning point. Okay, so this relationship can be approximated by a polynomial degree one turning point plus one, so second degree polynomial. Okay, so if the turning point is 1, then 1 plus 1. If the turning point is 3, then 3 plus 1. If the turning point is 2, 2 plus 1. Okay, in that way we can approximate the relationship between beta and the lag length using certain polynomial degree function. Okay, so how we can construct this model? Assume an infinite lagged model yt alpha plus beta 0 xt plus beta 1 xt minus 1 plus beta 2 xt minus 2 up to beta I xt minus I. This is what is called an infinite distributed lag model. Okay, now we can rewrite this distributed lag model into a more compact form. Okay, we can reduce this equation. How we can reduce this equation? This way we can reduce the equation. Okay, so yt is equal to alpha plus summation of beta I. So beta I means what? Beta 0, beta 1, beta 2, all this will be included. Okay, beta I xt minus I. Okay, plus u. So this is nothing but the more compact form of this equation. This equation is reduced to this equation. Okay, so instead of giving beta 1, beta 2, beta 3, what I am doing, beta I am taking beta I, and instead of taking xt minus 2 3 4, I am taking xt minus I. This is the most generalized form of a equation. Okay, now the step 2. So Almon's polynomial model is basically based on Weierstrass theorem. Weierstrass theorem is one of the most important theorem in mathematics. Okay, so this theorem says that on a finite closed interval, okay, any continuous function can be approximated uniformly by a polynomial of a suitable degree. Okay, so on a closed finite interval, any continuous function can be approximated by a suitable polynomial degree. Okay, so if you look at these models, beta I is equal to a0 plus a1 I plus a2 I square plus up to am I is raised to m. This is what Almon assumed that beta I means what? Coefficients. Coefficients can be approximated by suitable degree of polynomial in I, the lag in the lag length of the lag, the length of the lag. Okay, so suppose if you are having how we can approximate this degree? Look at this equation. Beta I is equal to a0 plus a1 into I plus a2 into I square up to am into I raised to m. This is what? This is a mth degree polynomial in I. Okay, it is assuming that m is the degree of the polynomial which is less than the maximum length of the lag. Okay, so if it is not clear, I will discuss. Look at these equations. Okay, so suppose this is the lag 1 2 3 up to 7. Okay, this is the beta coefficients. Okay, so this was the first beta coefficient, this is the second, it's lag coefficient. Suppose this is beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, beta 7. Okay, there are 7 lagged values are there, so there will be 7 coefficients will be there. Okay, so if you look at this equation, this is like a inverted U shape or reverse U shapes. Okay, so how we can approximate this kind of a function between lagged value and coefficients? Okay, this is how many turning points are there? One turning point is there. Okay, this is one turning point. Look at this is a turning point. Okay, so if there is one turning point, it can be approximated by two polynomial. That means using second degree polynomial, we can approximate the relationship between beta I and lag length. This is what is called Weierstrass theorem. Okay, so look at this, beta I is equal to a0 plus a1I plus a2I square. Okay, so this is what is called the second degree polynomial, a0 plus a1I plus a2I square. Suppose this is the second type of models. Okay, this is the beta i's, this is the lag length. There are 8 lag is there. It is no, first coefficient is this, second this, and after this it is increasing then decreasing. We have a cyclical pattern. Okay, so how many turning points are there? This is the one turning point, he is here, another one is here. Okay, so now you look at how we can approximate this. This can be approximated by the two turning points are there, so we can approximate it by this 2 plus 1 third degree polynomials. Okay, how we can express the betas using third degree polynomial? Beta I is equal to a0 plus a1 into I plus a2 into I square plus a3 into I cube. Okay, so this is the way we can express, we can convert or we can approximate the relationship between coefficients and lagged values, okay, using suitable degree of polynomial function. Okay, so this we are doing in line with the Weierstrass theorem. Okay, yes. So after that we are going to step 3. Substitute the equation from the second step to the first step. Okay, yes. Now what we are assuming that in order to explain this, we are assuming that betas follows the second degree polynomial approximations. Okay, well, we are assuming that the relation between these betas and lag length uh, is approximated by second degree polynomial. Then if this is the case, then how we can substitute these into the first equations. Okay, so this was our equation: yt is equal to alpha plus sigma xti, sigma beta I xti plus u. Okay, so instead of betas we have substituted these values. Betas is nothing but a0 plus a1i plus a2i square, because we are assuming here second degree polynomial. Okay, now multiply all these things with xt minus I. Okay, so yt is equal to alpha plus a0 sigma xti. Okay, a0 is a constant, this is summation notation, this is the variable. So how we can express a0, the constant value will come the first, so a0 sigma xt minus I plus a1 sigma I xt minus I, because I is not constant, I is a variable, so I into xt minus I plus a2 into I square xt minus I plus u. Okay, so what we have done here, we have substituted the value for betas, which is approximated by second degree polynomial, into our equation. Okay, now look at this equation: yt is equal to a alpha plus a0 sigma xt minus I, a1 sigma I xt minus I plus a2 sigma I square xt minus I. Okay, so what I am doing here is I am giving this value sigma xti is z0t, sigma I xt minus I as z1t, then sigma I square xt minus I as z2t. So instead of these big values or big equations or notations, I am giving just z0t, z1t and z2t. Okay, so how we can, now you look at this equation: yt is equal to alpha plus alpha 0 a0 z0t plus a1 z0 z1t plus a2 z2t plus ut. Okay, so you may have a confusion how to find out the z01 and z0t, because in the equation it is giving a1 a0 sigma xt minus I. Okay, so what we have to do is we have to specify the lag length and the degree of polynomial. Once you can specify the degree of polynomial and the number of lag length, then we can easily construct these z values. Okay, I will discuss it with later. Okay, so now suppose this, if you look at this equation, it is equal to alpha plus alpha a0 z0t plus a1 z1t plus a2 z2t plus ut. This is similar to a normal linear equations. This can be measured using OLS. Okay, but the problem is, actually we want to estimate this beta 0, beta 1 and beta 2, beta 3 like that, but here we are having a01, a02 and a03. Okay, so from this a0, from a0 values, okay, we can estimate the value of betas. Okay, so beta 0 will be equal to a0. This is not alpha cap 0 but a0. Okay, a0. Beta 1 will be a0 plus a1 plus a2. Beta 2 will be a0 plus 2a1 plus 2 square a1. Okay, and beta 3 is equal to a0 plus 3a1 plus 3 square, okay, 9a square. Okay, similarly we can calculate all the remaining values. Okay, so suppose if m and k is specified, suppose m is equal to 2, that means we have a second degree polynomial approximation and the number of lag length is equal to 5, then how we can construct is z, okay, z0t is equal to sigma xt minus I, where I is equal to 5. Okay, so xt minus 1 plus xt minus 2 plus xt minus 3 plus xt minus 4 plus xt minus 5. This is the z0t. Okay, now z1t, z1t is what? Sigma I xt I. Okay, so xt minus 1, 1 into xt minus 1 plus 2 into xt minus 2 plus 3 into xt minus 3 plus 4 into xt minus 4 and 5 into xt minus 5. Here I is equal to what? I is equal to 1, 2, 3, 4, 5. Okay, because you look at the equation a0 plus a1 into I plus a into I square plus a into I cube. It will go, the polynomial equation will go like that. Okay, that's why this is the a0. We are not multiplying any values. Here we are multiplying with 1, 2, 3, 4, 5. Okay, and here what we are doing, z2t sigma I square. Okay, so this is 1 square xt minus 1, 2 square 4xt minus 2, 3 square 9xt minus 3, 4xt 16xt, 5xt 25xt. Okay, so in this way, suppose if we have given this m and k, we can easily construct this z value such z0, z2, z1 and z2. Okay, so but the problem is how we can specify the lag length. Okay, so we have to specify the maximal lag length in advance. Okay, but if we choose fewer lag, it will lead to the omission of the relevant variable, and if we choose more lag, it will lead to inclusion of the irrelevant variable. Okay, so what we have to do, selecting an appropriate lag is the most important problem in econometrics. Okay, so there are certain methods to choose the appropriate lag based on your data, such as archaic information criteria AIC, Shaw's information criteria, Hannan-Kuhnen criteria. Okay, so there are such kind of criterions are there in econometrics. Based on that criteria, you can select appropriate lag length. Okay, similarly, we have to specify the degree of the polynomial m. Okay, but as per this theory, the degree of polynomial should be at least 1 more than the number of turning points in the curve. Okay, but we may not know the number of turning points in advance. Okay, and therefore this number of, or this approximation is basically a subjective matter. Okay, so but sometimes the theory may suggest a particular shape in the some cases. Okay, in most of the cases, if you have a proper theoretical support, then it may suggest certain ideas about the relationship between lag length and coefficients. Okay, but in other cases, we don't have how many number of turning points are there in these equations, so we don't know that. Okay, so choosing the degree of polynomial is largely subjective. Okay, so this is the major features of this data, this Almon distributed models. Okay, so let me discuss one more. Okay, so this model, Almon distributed model, is basically a model to overcome the limitation of Koyak model. What limitation? The limitation is Koyak model assumes all beta coefficients will decline in a geometric in a geometric progress of in a geometric process. Okay, but it may not be a case. Sometime beta coefficient decline in the first, then it may decrease, it may increase, or it may increase first and then it may decrease, or it may have a cyclical pattern. Okay, in such situations the Koyak model will not work. So what is the suggestions made by this Shirley Almon? He suggested uh, you express the relationship between betas and the lag length in a functional forms and try to fit a suitable curve to reflect these relationships. Okay, and after fitting this suitable curve, you look at the turning points in this curve. Okay, so as per Weierstrass theorems, we can say that as per Weierstrass theorem, we can approximate the polynomial degree at least one more than the number of turning points in the function. Okay, so how we can do that? First, you assume an infinite lag model. Yt is equal to infinite lag model is there. Then you just reduce the equation into a more compact form. Then you apply Weierstrass theorem. Okay, then you find out the relation. Then you find out number of turning points. And after finding out the turning points, you express the turning points in an equation, and that equation you substitute in the original equations. Okay, so this is the equation for this functional form. Here we are assuming one turning point, inverted U model. Okay, so there will be one turning points. So alpha plus k, alpha 0 plus alpha a0 plus a1i plus a2i square xt minus I plus u. Okay, so if you multiply this sigma and xt minus I with a0, a1i and a2i square, we will get this kind of an equation. Okay, from this equation, this you consider this as a z0, z1 and z2. Okay, now it look like a linear equation. Using Euler's, you measure or you estimate this parameter. Okay, so by estimating this parameter a0, a1, a2, a3, we can back to our original model. In original model, we have coefficient like beta 0, beta 1, beta 2. Okay, that we can find out from these equations. Okay, then you don't need to worry about how we can construct z0, z1 and z2. It's not an issue. If you have m and k, if you can specify m and k in advance, then you can construct z01, z02 and z03, or z0, z1 and z2. Okay, but it has many problems. The most important problem is the lag, how we can specify the lag length and how we can specify the degree of polynomial. Okay, now let us discuss and how we can do these problems using some real example. Okay, we will examine that. Yes. Yeah. Okay, so look at this data. We have a data on inventory and sales. Okay, then in macroeconomics you have learned that inventory is a function of sales. Okay, if the sales is increasing, then they have to keep more inventory. Okay, inventory theory of investment. Okay, so we have a data from 1954 to 1999. We have a huge set of data, almost 46 years of data is there. Okay, So what we have to do, we are assuming that here the lag length is k is equal to 3 and m is equal to 1. So 1 plus 1 is equal to 2, second degree polynomial. Okay. So here look at this data here xt minus. So what we have to do first, we have to construct this z01, z0, z1 and z2. How we can construct? Using the past values of your independent variable. So the independent variable says the sales is x or xt. You take its first lag, second lag, third lag. Okay. So here values are not there, value will not be there, value will not be there. Okay. Yes. So these are all we have constructed xt minus 1, xt minus 2 and xt minus 3. Okay. Then first we will construct z0t. What is z0t basically? It is nothing but xt minus 1 plus xt minus 2 plus xt minus 3. Okay. Yes. Now z1. What is z1? Z0, the xt minus 1 plus 1 into xt minus 1 plus 2 into xt minus 2 plus 3 into xt minus 3. We are getting these values. Okay. Then what is z2? 1 into xt minus 1 plus 2 square, I square is 2, I is 2, 2 square 4, okay, plus 3 square 9. Okay, so we have constructed all these z01, z0t and z03. After this, what you have to do, you do an OLS, okay, by making inventory as your dependent variable and all these variable as your independent variable. Is it okay? Yes, it will look, suppose after estimate this, it will look like this. Okay, this intercept is this. Okay, this is the slope, the z0, coefficient of the z0, coefficient of z1, coefficient of z2. Okay, so once we have estimated this model, what we can do, we can construct beta 0. Beta 0 is nothing but a0. This is basically what, this is a0, a1 and a2. Okay, so beta 0 is what, a1, a0, beta 1 is what, a0 plus a1 plus a2. Okay, now what will be the beta 2? 1 into a0 plus 2 into a1 plus 3 into a2 minus 2.10. What is beta 3? 1 into a0 plus, but 1 square will be 1, then 2 square 4 into beta 1 a1 plus 3 square into a2. We are getting minus 7.692. Okay, so beta 0 is 8.13, beta 1 is 2.24 and beta 2 is equal to minus 2.10 and beta 3 is equal to minus 7.6912. Okay, so this way we can develop, or we can estimate, or we can develop, or we can construct z0, z1 and z2, and we can estimate this model, and we can derive the original coefficient from the coefficient of z. Okay, so this is what is called Almon polynomial distributed lag model. I hope it is understood, and if you have any doubts, you can mail me or you can send me the message. I will clarify your doubts. Okay, so thank you.